Hello, welcome to Mr. Jesse's video tutorial in physics. This problem came out in the system-wide quiz in advanced physics for 2015-2016. Four capacitors are connected to a 35-volt power supply as shown in the figure below. The capacitances of the capacitors are C1, 3 microfarad, C2, 5 microfarad, C3, 8 microfarad, and C4, 10 microfarad. The first thing that we need to do is to simplify or reduce this complex combination of capacitors. So let's redraw it. We have here our 35-volt battery. This is our C1. And we have here our C3. This is our C2. And then we have here our C4 connected to the terminal of the battery. Let us just label them first. We have our C1, C2, C3, and C4. To analyze or to reduce this complex combination of capacitors, we must be able to flow or to trace the flow of charge. So if we consider that charges will flow from the negative end of the terminal, go to the positive end of the terminal, we have to analyze it per junction. So as electrons flow from the negative towards the positive, it enters this first junction. So we could actually see that charges could either go up or continue towards the right. So if we're going to look at the charges that are moving towards the right, we could conclude that these charges, or we could see that these charges will go straight through C4, then to C2, and enter this junction over here. Therefore, C2 and C4 are actually in series. From that analysis, we could then redraw our circuit into something that's going to look like this. Let me just change the colors. So we have here our battery. Then this will be our C1. Over here will be our C3. And here would be our C24. Let me just label them. That's our C1. This is our C3. And this would be the series combination of capacitors 2 and 4, or we call that C24. And from here we could see that as charges move from the negative end of the terminal, they would now enter this junction. We could see that they could either go up or towards the right. And then for the charges that goes up, for these charges, they would go through capacitor 3 and have that junction there. And for the capacitors that would go to the right, they would pass through capacitor C4 and also meet at the junction. Therefore, capacitors 3 and capacitors 2, 4 are actually in parallel. The two are in parallel. Moving further, we could redraw the further reduction of the combination of capacitors into something that would look like this. So that would be our battery. This is our C1, and this would be our C3 to 4. So let me just label that. This is our C1, this is our C2, 4, 3. And clearly from this combination, we could see that capacitors C1 and C243, they're actually in series. As charges move from the negative end of the terminal, they would just flow through the two capacitors to reach the positive end of the terminal of the battery. And then it would be so easy to solve for the equivalent capacitance of that combination. So to solve for the total capacitance of the combination, since C1 and C243, they're actually in series, and we could just say CT is equal to the quantity of 1 over C1 plus 1 over C243 raised to the power of negative 1. And we have to remember that capacitors C243, C243 is just actually the parallel combination of capacitors 3 and capacitors C24. So we will just have C3 plus C24. And we also have to remember that capacitor C24 is just the series combination of capacitors 2 and capacitors 4. So we will have C C24 is equal to the series combination of capacitors 2 and capacitor 4. So we will have C24 is equal to the quantity of 1 over C2 plus 1 over C4 raised to the power of -1. We substitute of the values to obtain our total capacitance. Now, to solve for the charges stored in each capacitor as well as the potential difference in each capacitor, it is very essential that we have to work our way backwards. It needs patience to actually work your way backwards to solve for the charge and the potential difference in each capacitor. So now that we have the total capacitance, then we could actually solve for the total charge, which is just equal to QT, and that's equal to total capacitance multiplied by the total voltage, and in this case total voltage is equal to 35 volts, which is the power supplied to the combination of the capacitors. And since our total capacitance is actually composed of C1 and C234 that are connected in series, then we could say that the Q234 is just equal to the total charge, because that's actually a property of a series circuit. And similarly, the charge in capacitor 1 should also just be equal to the total charge, or we say Q1 is just equal to QT. And now that we have capacitance and we have the charge, then we could actually solve for the voltage across capacitor 1, which is actually V1. And also, since we have capacitance 234 and we also have the charge 234, then we could solve for V234. Now remember that capacitance 234 is actually a parallel combination of capacitors 3 and 4. So let's move our way backward into the next figure, which is this. So we could actually carry over the information that the voltage across capacitor 3 and capacitor 24 would just be equal to voltage 234, because C3 and C24 are in parallel. So we can actually have V24 is just equal to V234, and also V3 is just equal to V234. And since we have our C24, we also have our V24, then we could actually solve for Q24. And also, since we have our C3, we have our V3, then we could also solve for Q3. Moving on, since capacitor 24 is actually a combination of capacitor 2 and capacitor 4, then we could actually carry over the information that the charge in capacitor 4 is just equal to the charge in capacitor 24. Also, the charge in capacitor 2, or Q2, is just equal to the charge in capacitor 24. So then we have our C4, we have our Q4, then we can solve for V4. Also, since we have our C2, we have our Q2, then we could also solve for our V2. And then we will be able to obtain all the things that are being asked in the problem. On the red box are the answers to the questions that are associated with this problem. That will be all. Thank you.